So welcome back. Today we'll talk about dielectrics and polarizations. Okay. Dielectric, as the name suggests, it has got two types of electricity. One may be a positive and another negative. It all depends upon what the molecules orientation, etc. is about. Okay. The dielectrics are non-conducting substances where the number of free charges per unit volume, which I have written as n, that goes to approximately equal to 0. Okay. In the conductors, very large free electrons are there, etc. etc. Polarization. Okay. Polarization is a word which is well known to us. There are so many kinds of polarizations, but we know about the poles of the earth. The earth moves around an axis which passes through the north and the south poles, and there is the magnetic poles, north and south, etc. So it means that there is a kind of an orientation. Okay, they subscribe to this kind or that kind and that kind or that kind, etc. So that's called polarization. Okay. So first of all, I'll go back and let you know why the electric field inside a conductor, which I said is equal to 0. Okay. Just because the potential profile inside is constant everywhere. But today we'll see as to what happens when a conductor is put in an external field, E0. Okay, you can see that this is a uniform electric field and external field, and this is a chunk of a conductor. So what happens? That, let's say that inside also there is an electric field E0. But no sooner than this field is applied, the external field is applied, the free charges, free negative charges, they move from here to here. As many have just shown 8 charges over here and 8 charges over here, so this phase becomes negative and this phase becomes positive. So the charge density is like this. What happens? So internally there is an induced system by which there will be induced electric field. Not suddenly, but it takes little bit of time. Little bit of time. That means very small time. Before, what happens is that the internal field and the external field, they become equal and opposite and cancel out the effect, so the net field inside is equal to 0, which I told you in the previous lecture that it is equal to 0. This is about the conductors. But in the case of dielectrics, the molecules are randomly situated. There is thermal agitation that may be going on. But when an electric field is applied, there comes an induced dipole moment. And due to this sigma p I am writing because of polarization, there are positive charges on this side and negative charges on this side, and the electric field is the same like before. Okay, and there is an internal field which is generated, which has been shown to be of a length less than this length. That means the sum of the two fields which are opposite to each other is not equal to 0, it's rather in the same direction. Okay. So that means that the field are outside and outside, but inside, within the dielectric, the field gets reduced. What happens? Because there is an opposition and the net value is not equal to 0, there is field reduction. And this field reduction is a function of the nature of the dielectric. What does that mean? Okay. You are my nephew or my niece, my sister's son or daughter. On a festival like Diwali or like Eid, I'm visiting your place. What I do is that while partying, while patting your backs and appreciating you and your mother, I part with 500 rupees to you and also to your mother. Your budget is maybe 300 rupees per week or something like that. And your mother's budget is several thousand rupees which she has been spending. She will be nostalgic, the brother has visited, okay, she will be happy. But you will be very, very happy because you add a substantial amount to your kitty. And in your mother's kitty, that is a small fraction, maybe 2%, 3% of what she has. So now this is exactly what is going to happen. Let's take the molecular level. The molecular level is you and your mother. Okay. You are, we'll call like non-polar molecules. Here I have a molecule of hydrogen, okay, or I can have a molecule of oxygen, and here I have a molecule of oxygen, an atom of oxygen, and like this they are in the same line. They are non-polar. Means their centers of positive and negative charges are the same. There is no separation between them. So A is equal to, or 2A is equal to 0 in this case. Nevertheless, when they are put in the electric field, okay, and this kind of thing happens, then their centers are separated, okay, and they are happy to have a dipole moment vector which was not there before, okay, like you obtained 500 rupees from your mama, okay, and you were very, very happy about it, that my kitty has increased from 600 rupees to now 1100 rupees, like that. But there are molecules like HCl. In HCl, this H and Cl, they have a kind of give and take kind of thing. An extra electron in the outermost orbit of chlorine will go and satisfy the hydrogen. So there is a polarity. There is a dipole moment exists from before. And similarly, one of the most beautiful things that we have is water. This water has two hydrogen attached to an oxygen. Okay, and they become positive, and of course it will have a center over here of these two, and they are positive. I have not applied any electric field, etc. But we have a polar molecule. The dipole vector is shown to be like this, and the dipole vector is shown to be like this. In polar molecules, they are kind of permanent, okay, dipole moment vectors they have. And like in the case of your mother, their kitty is, your mother's kitty swells a bit, a 1% to 2%, like that. She will be very happy to say, Bhaiya came to, my brother came and he gave me this and that, and my Mecca is very good, okay, in this, that. But at the same time, that 500 rupees are not going to make her as happy with 500 rupees that I've given to you. Similarly, the effect of the polarization that will occur, the reorientation of molecules that is going to take place in external electric field is going to be more in these cases than these cases. So we'll say that the value of the dipole moment associated with the polar molecules is not going to change much. However, the word permanent is not good. You know why? Because there is only one thing which is permanent, and that is change. Okay? Nothing else is permanent. Sometimes people say only God Almighty is permanent, else everything is not there. Okay, so one time will come when the time will not be there, when the space will not be there, etc. etc. Okay. So we talk more about that in the. So let's see what happens to the non-polar and the polar molecules when they are subjected to an electric field. Okay. Taking a page, I have just drawn the case of the non-polar and the case of the polar molecules. Okay. Without electric field, subjected to an electric field. Okay. Which is from left to right. Okay. Now, what happens? Let's talk about the non-polar molecules, which don't have a permanent dielectric moment vector. Negative charges go to the left. Look here. The charges are like this, plus, minus, like that. Okay. Without that. Now, when the field is applied, they get a bit elongated. The positive charges go to the right and the negative charges go to the left, like it has been shown over here in this set of boxes. Okay. It happens. The positive and negative charges in the molecule are displaced. This displacement stops when the external force on the constituent charges of the molecules is balanced by the restoring force. One force is like this and the other force is like this. The two forces become equal. So there is balance. Are balanced by the restoring force. Look here, this is very important. Due to the internal fields in the molecule. Okay. So there is a balance. Ready. So what happens? The non-polar molecules, they develop induced dipole moment vector. Induced. Induced means forced. They, because of something. Okay. There is a reason for that. And that reason is induction. Okay. So the dielectric is polarized by the external electric field in such a way that the dipole moment vector which is there, which is developed over there, the two halves, the P and E, are in the same direction. Okay. So P cap is equal to E cap, and also that the polarization, the P, is proportional to the magnitude of the electric field. Okay, such dielectrics, okay, they are called linear isotropic dielectrics. Isotropic means same in all directions. Okay, there are no preferred directions, then we say that the things are isotropic. In the case of non-polar molecules, you can see that there is a random distribution. Things are randomly arranged and they are vibrating. They are vibrating. They are not stable in the system. There is nothing to drive them. They can go anywhere, like this, random. Why? Because they are subjected to a temperature, okay, and the temperature is manifested in the average kinetic energy of associated degree of freedom. There may be so many degrees of freedom, so there is a average kinetic energy, and that manifests itself in the form of the temperature. Okay. Later on, what happens when the electric field is applied, then you can see that the molecules, they orient themselves. Okay, the positive charge on this side, negative charge on this side, and these polar molecules are like your mother, and this is the non-polar molecules are like you. Okay, so there is substantial change in this value, but for example, when I say that you have 600 rupees with you and I give you 500 rupees, so it becomes almost double. But if your mother has 60,000 budget and I give her 500 rupees, okay, the same with the same love and affection, then it's only a small change, okay, almost 1% in her kitty. Okay, but anyway, they are oriented along the electric field that is there. Okay, so we were discussing the polar molecules. Okay, the polar system. The polar molecules develop a dipole moment vector in the external field due to the alignment of the molecules with the electric field, giving rise to a net value of P. Okay. So this brings us to define what is polarization. Okay. In doing so, what actually happens is, I've just shown this that this side is the negative at the surface, near the surface, this side is the positive, and the other molecules are oriented like that. Okay. So if I just look at this, then this side I have all positive charges, and this side, because of the orientation, we have all negative charges. So I have a surface charge density plus sigma p, and here minus sigma p. But inside, anywhere, if we take as to what is the density in the volume, that in the volume it will be equal to 0 within the volume. As many positive charges, the same number of negative charges are there in a certain volume element that will take inside. But the surface, the orientation is like this, so the negative charges on one side and the positive charges on the other side. Okay. Because of this, the positive charges here and the negative charges on this side, there is an electric field internally which is produced, okay, and the material gets polarized. Polarization, capital P, is defined as the dipole moment per unit volume. For linear isotropic dielectrics that we have talked about, whether they are polar or non-polar, the polarization capital P is equal to chi E into capital E. What does that mean? It simply means that if we plot the value of the polarization as a function of the value of the electric field, then there will be a straight line, because it means that the P is proportional to E and is equal to this chi E. Chi is again a Greek letter, the capital letter, and is called electric susceptibility of the dielectric medium we are talking about. What? Electric susceptibility. Susceptibility means how much prone it is. Okay? Like, for example, for children younger to you, in the summers, the mothers will say, don't go there, there is sun, and you may get a sunstroke or something like that. So what you are there, you are susceptible to certain changes. So susceptibility is such that the medium is susceptible to the polarization which is taking place over here. Okay. With that, I call it a day. Okay. So in the last lecture we had talked about the conductors and their behavior in the electric field. Today also I started with the conductors, explained to you why the inside of the conductors under a steady state condition they have a zero electric field, and then introduce you the dielectrics and talked about the polar, non-polar and polar molecules, okay, with the help of some example where you were involved along with your mother, my sister, okay, and we talked about things like dipole moment that develops because of the polarization, and also about the dipole moment which exists as a permanent dipole moment in the case of certain molecules like water, and the most interesting thing is water. Okay. In the dipole condition of the dielectrics, actually there is something we'll talk about, epsilon r. I told you that epsilon, oh man, no good. Epsilon r, relative, a number which is called relative. Epsilon is permittivity. Okay, this epsilon r is related to many things associated with that, and the water has got an epsilon r very high value, about 81, so that whatever force we have, like 1 upon 4 pi epsilon of water, Q1 between two charges, Q1, Q2 upon R square, this force is reduced by this factor, because epsilon of water is equal to epsilon r into epsilon naught, and epsilon r is approximately equal to, in the case of water, it is actually equal to about 81. That means when you put things in water, then the forces that are there, they become, and that is why water makes things dissolve in water very easily, because the value of epsilon r is high enough. Okay, we'll talk about that later on when we talk these things in detail. Thank you very much, and I love to listen to your questions, which you are not sending to me. And you question and we answer, because that desk, the person who is sitting on the desk is not happy with you. So make him happy, make her happy, and they will be able to answer the question with my help. Thank you very much for the day.